let's consider an air capacitor, 255 nanofarads. It's going to stay connected to a battery, power source V. The energy stored in the capacitor is 20 microjoules. Then a dielectric is inserted and the energy goes up by 30 microjoules. So what's the potential difference between the plates, the potential difference, and what's the dielectric constant that results in a 30 microjoule increase in the energy? So we stick in the dielectric. We had 20 microjoules. It goes up 30 to give us 50 microjoules. Well, the potential difference is simple, and it's going to stay the same because the V, the source, is still connected across. But let's look at the original configuration to determine what it is. Knowing that the energy, which is given, 1/2 CV squared, which is 20 microjoules, V is square root of 2U over C. And so plugging in the numbers gives us 12.5 volts. Very straightforward. Now, what's the dielectric constant K? Well, the energy that is now contained in the capacitor is 1/2 CV squared. But that, the only thing has changed is the C. The C has gone up by the dielectric constant K since V is the same. So it's 1/2 KC0 V squared. So that's K times U0. So if we replace this with if this was just C0, the original energy is 1/2 C0 V squared. So this is K U0. So K is the ratio of the energies. We've seen that before. And it's now 2.5. Okay, a very straightforward application of these formulas. Got a parallel plate capacitor. Dimensions given, spaced 0.58 centimeters apart, connected across 50 volts. Let's find the various pertinent physical quantities, like the capacitance, which is epsilon 0 A over D, which is epsilon 0 A over D, 49 picofarads. How about the charge on the capacitor? C times V. 49 picofarads times 50 volts gives us 2.47 nanocoulombs. What about the electric field? Electric field is volts over distance. 50 over 0.0058, 8620 volts per meter electric field. And the energy, 1/2 CV squared, 1/2 CV squared, 61.3 nanojoules. So there it is. Now that was with the power supply connected up. Now we're going to disconnect the power supply, and then we're going to separate the plates. We're going to double the distance, and let's get the new physical quantities. Okay, so dimensions are the same, but this time we separate the plates to 1.16 centimeters, doubling it. The battery was disconnected at first, so there was no chance for charge to leave or enter. So the charge is the same as it was. C, geometrically, what's changed? Oh, the distance has doubled. So the value is likewise diminished. It's cut in half. 24.5 picofarads. Charge, C times V. Now we know that the charge has got to be the same because none could leave or enter. Let's just see if the formulas make sense. C is C0 over 2. The V is twice V0, and certainly, sure enough, 2.47 nanocoulombs. Now the electric field is based on the surface charge density of the plates for parallel plates, so that shouldn't change either. Let's see, V over D, twice the voltage over half the distance. Sorry, double the distance. They cancel. 8620, just like before. The energy, Q squared over 2C. Q squared over 2C gives us 124 nanojoules, so the energy is doubled, and it stands to reason because it took energy from I should say it took an external force, positive work, to take that plate and move it to its new position, which increases the electric potential energy of the system. All right, so now the battery is attached to the plates the whole time as we separate the plates, which forces the potential difference to remain at 50 volts. So V is the same. Now what happens to Q, E, and U? Well, let's find out. First of all, what about the capacitance? The geometry hasn't changed. The physical quantities that we add or subtract from this don't matter. It's still 24.5 picofarads after we separate it. Q, CV. Now, the power supply remained attached, so there is the potential, no pun intended, for charge to come or go to from the power supply. So CV, the 50, 1.25 nanocoulombs. So indeed, the charge has gone down. Charge has left the capacitor and gone into the power supply. How about the electric field? Well, it should follow. V over D. The V is what it originally was. The D is separated by twice. And so the electric field goes down. And finally, the U. 1/2 CV squared. We have the values here. The V, which is 50 squared, causes the potential energy to be considerably less than it was in the previous example. So that's how that works for keeping the power supply attached. Recognize there's a big difference between the two situations. It's always very important with such problems to ask yourself, is the power supply attached or has it been disconnected prior to doing the plate separation change? And that will lead you in the right direction.